Today, I'm talking about Thread. That is the fancy new wireless protocol that's supposed to bridge Internet Things devices with the Internet at large. So, gone are the days of all of these possibly open, possibly proprietary home automation standards where we can only have 254 devices because clearly someone didn't think out the addressing. No, all of that's out of here. Now we have nice IPv6 connectivity across low power, low bandwidth sensor networks. And that means we can bridge these low power, low bandwidth sensors straight onto the internet or IPv6 networks at large. Now, Thread is often talked about with the new Matter home automation protocol, but it's actually a pretty distinct separate thing. Matter is a protocol that runs over IPv6, and it allows home automation and other Internet of Things devices to communicate with each other and with their controller. However, being that it runs over IPv6, it needs a transport. We could use traditional wired Ethernet, which is very reliable, but obviously it needs wires. We could use Wi-Fi, and if your devices are powered, that's probably a perfectly acceptable thing, but it's not good enough for battery-powered, low-powered stuff. So that's where Thread comes in. Thread takes the IEEE 802.15.4, MAC, and PHY, and builds a whole IPv6 network on top. So if you are into IPv6 routing across a low-power, low-bandwidth sensor network, and specifically how to set this up using entirely open-source software. So I'm running open-source firmware on my dongles, I'm running OpenThread Border Router, OpenThread in general, and I'm hooking it all up to Home Assistant. If that sounds good to you, then come along on this adventure. So before I get too far in the video, I thought you guys might appreciate a demonstration. So I got a whole bunch of these guys. These are Nordic Semiconductor NRF52840. Yeah, 52840 dongles. They're $10 each from DigiKey, which I don't think is that expensive. This chip is also a really common example chip for Thread. The dongle is the cheapest way to get this chip, so that's what I used. Now this box here is actually running Proxmox, so I'm running virtual machines in here which run Debian. And actually the installer is picky enough that it doesn't work on the Debian cloud images. It needs the real full fat Debian with the full kernel. Now this is mainly useful just for testing because I'm spinning up and tearing down VMs so frequently. For my actual deployment, I've got a Raspberry Pi 4, and that's running Raspberry Pi OS 64-bit, which is just Debian. So all the scripts work the same on Raspberry Pi Debian or regular x86 Debian. Now this box is my Kali PC, which I use for packet captures, and this is acting as my client. This one's running bare metal, but it's still Debian based, so all the scripts still work. So here on the client, I've got the daemon running. So if I run IPA, you can see I have WPAN 0, that's my personal area network, and I got a number of IPv6s here, including a global unicast. So that one can get me to the internet. And then I don't actually have Ethernet or Wi-Fi, I just have the Thread network. So then up here in the Thread console, I can run IP addr, and these are my local addresses. If I run netdata show, I can see the routes I've got. So B00 is my border router. He's sending out this guy, it's a route, and etc. So I do want to emphasize in this video that Thread and Matter are two separate things. So Matter is a home automation protocol that runs over IPv6. And Thread is a IEEE 802.15.4 based personal area network protocol, which provides IPv6 transport. So Matter requires IPv6. It can get that from wired Ethernet or Wi-Fi, but for lower power, lower bandwidth stuff, Wi-Fi is too much work, and I can't go to sleep long enough. So Thread, based on 802.15.4, gives it the same IPv6 transport it's always wanted, but it doesn't have to deal with Wi-Fi. It can use lower power 802.15.4 stuff. But just because it can run Matter doesn't mean it can only run Matter. So in this case, I've set up my whole network with IPv6 global unicast addresses, which is actually not normal. So most Thread devices can't talk to the internet because they don't have an internet routable address. But the Thread protocol allows you to use internet routable addresses if you want to. And you can even do NAT64 to get access to the IPv4 internet if you want to. OpenThread supports all of that. So this guy is going to browse my website over Thread. So just to prove that it'll work, I can do a ping. This is a well-known DNS server. So my ping time is not fantastic, but it's not awful. And let's pull up Firefox and load my website and see how bad it is. So lots of packets are going across the mesh here. I recognize the 2A01 address is my own website, so my website should load relatively quickly. This is painful. There we go. Okay, we're up. We've loaded. So I was able to establish a TLS connection and pull down the full contents of my index page on my website, which, to be fair, is not a lot of data. My website is entirely statically generated, so there's no JavaScript coming or anything. It's just the HTML and some of the CSS resources. Let's try another thing. We're going to try fast.com. Let's see how bad that is. So we've loaded pretty quickly, but can we get bandwidth here? Ooh, 28K, okay. 28K is not bad. 36K, 45K. We're doing better. So we're at about dial-up speeds here. Currently we're getting 67 kilobits, which is pretty awful, but that's about what we expect over 802.15.4. Now again, home automation stuff doesn't need that much bandwidth. What it really needs is low power PHY, and 802.15.4 has that compared to Wi-Fi, so it's good. So anyway, I got a couple different things that are going on in this video. First of all, we have to compile a firmware image for the dongle to use it as a remote radio. So the thread stack actually runs on Debian in these systems. The radio firmware is just bridging 802.15.4 onto USB. So we're going to compile that firmware, get it loaded onto here. That's a bit of a tricky process thanks to Nordic Semi's toolchain. Once we have all the dongles flashed, we can run the OpenThread Border Router, which will bridge between Thread and the rest of the world over either Wi-Fi or Ethernet. In this case, I'm doing Ethernet. Once we have one border router, we probably want a client, so I'll show you how to set up a client as well using the OpenThread daemon. You can, of course, use all of your Thread clients using Matter, but Matter is not in the video today, it's just Thread. And then finally, we're going to show how routing works. So if I set up multiple border routers, multiple routers in general, we can route packets across the Thread network, hop by hop by hop. And we can have more than one border router, so if one of them fails, we can still get connectivity to the rest of our network. So be sure to check the chapters somewhere down here to skip to what you're interested in. It is probably going to be quite a long video. Some of these technical topics are really picky, so stick with me. So before I get too deep into the weeds on how to actually set up a Thread network, I think it's important that we understand the topology we expect from a Thread network. What sort of devices we'll see, what role they'll have, how they route, how they communicate, things like that. So in general, on a Thread network, we have two types of devices or device classes. Those are devices which are routers and devices which are end devices, which are not routers. Breaking that down a bit more, we have a couple different acronyms for these. So in routers land, we have backbone routers or BBRs, border routers or BRs, we have routers which are just routers, and we also have end devices which could potentially be a router, or router eligible end devices, or REEDs. Those guys are still an end device, but they hope to be a router someday, and maybe they will be. And then for end devices, we have full end devices, minimal end devices, and sleepy end devices. And this generally refers to the power and communication state of these devices. So full end devices may be powered on all the time. Minimal end devices have a lot less logic. Maybe they go to sleep a lot. Maybe they don't. Maybe they're just not very smart. Sleepy end devices, they go to sleep a lot. So whatever router is managing that sleepy end device needs to be aware that it has to wake it up first or wait until the next time that it wakes up on its own. So here's an example of a bunch of Thread devices I got just kind of chilling. So I have my border router, which is going to manage the network. I've got my two blinds. These are my sleepy end devices. I've got a minimal end device. Maybe this is a button or something. And then I got two light switches. So these might be router eligible because they're powered on all the time. One of the minimum qualifications for being a router is that routers must be powered on all the time. So they can't go to sleep, but they always have to be listening for messages. This generally means they're not battery powered. So devices like smart light bulbs, light switches, those kinds of things are very often eligible to be routers. So basically these guys are going to be broadcasting mesh link establishment all day. So each of these guys is just going to send out wild MLE messages trying to find neighbors. And eventually they're going to find the nearest router, which in this case is our border router. So he made a link, he made a link, he made a link, he made a link, and he made a link. Now initially, when a node joins the mesh, it always does so as an end device. Even if it's router eligible, even if it's a border router, it's going to start off as an end device and then get promoted from there. That means it has to find, via mesh link establishment, a peer to be its parent. And so we identify every node of the mesh by their parent. So we have a hex identifier for the router ID, and then we have a suffix after that that is the child ID off of the router. And when we're doing routing, only routers are part of the routing. So by taking an address that is a parent plus a child, we know we have to find a route to that parent, and then that parent will have a list of all of its direct end device children to send to. So this guy here is going to say, you know, these two guys are eligible to be routers. Maybe we should promote them to be a router. So let's go ahead and promote those guys. Bring in some router boxes. So now these guys are routers. They can be part of the routing table. And maybe some of these end devices will find a better link to this router instead of this router. So maybe he wants to move over here. Maybe he wants to move over here. And then maybe also these guys can route directly with each other. Maybe they're close enough for that. So now we've got a triangle of routes here. They've got their end devices. And these guys up here that are routers, all three of them, are going to maintain the routing table. And their end devices don't have to be part of routing at all. So now that we've promoted these router-eligible end devices into full-on routers, we've formed a mesh. So all of the devices that are router-eligible, if we don't have too many of them, will become routers eventually. It'll take some time to get promoted. Then we will have a nice strong mesh. All of these devices that are able to talk to each other directly over the air will establish a link, a peering relationship with each other. And once they peer, they can share their view of the routing table and how to get to every other router. We've also simplified the work a lot for end devices. So end devices only have to know who their immediate parent is, and then that becomes part of their IPv6 address en route. And then to get to any child device, we've encoded the router ID and the parent and the child ID into their IPv6 address. So if I want to go to node, say, B001, I know that's router ID B and child 001. So I look into my routing table, I can find a route to router B, and then router B will have a route to every other router, but also a direct link to all of its children in case child 001. Coming back to my drawing here, that might be B00, which would make this guy B001. This guy here, maybe he is 8000, and this guy will make him, I don't know, A000. And then their corresponding end devices just get a 1 on them. A001 and 8001. So notice here that the router has an ID, which has lots of zeros on the end of it. This is essentially its IPv6 address, or its suffix. And then the end device gets an 001 on the end. So in order to route, so if this guy here wants to route from A001 to B001, all he has to worry about routing to is his parent, which in this case is a router. And because it's a router, it knows where to get to A, 8, and B. So it can find then 8001, or in this case, router 8000, who then has a list of all of its children, in this case, 8001. And so since we've taken this 16-bit routing locator, or RLOC, and added it into the end of our IP addresses, now every node can be uniquely identified over IPv6. Then we can speak plain old UDP, or even TCP if we wanted to, over this network. Only our more privileged routing nodes have to deal with the complexity of managing a routing table, and our sleepy nodes can go to sleep. Their parent will manage their packets for them. And for those of you math nerds out there, the routing protocol in Thread is based on the distributed Bellman-Ford distance vector routing algorithm. And if you think that sounds really cool, you might like the sponsor of today's video, Brilliant.org. Brilliant is a simple platform with thousands of interactive lessons on math, science, data analytics, coding, all kinds of topics like that. You can practice every day. Brilliant's hands-on approach means all of the lessons are interactive. You can actually play with the math and science right on the app or in your browser. This approach is proven to be 6 times more effective than just watching lectures. I tried out their course on linear algebra, which is a topic that I'm particularly fond of, and I found it to be very easy for a visual learner. I tend to like problem solving through doing things. That's why I've worked a lot in engineering my whole life. And I found that this sort of lesson style motivated me very well. So maybe you're not into linear algebra like me. Maybe their programming courses will be better for you. They have a whole series on thinking like a programmer, how to break down large complex topics into manageable chunks, and the basics of programming in Python as well. Try everything Brilliant has to offer free for 30 days. Use my code brilliant.org/AppleArdsAdventures, or my QR code somewhere down here, or my link in the description. Plus, you get 20% off an annual membership. Thanks to Brilliant. Now back to the video. So maybe a bit of simulation will help reinforce this thread network concept. So this is OpenThread Network Simulator, part of OpenThread, and I've got this network set up here with hexagons. These are routers. Circles are end devices. So this guy is a full end device, this guy is a minimal end device, and this guy over here is a sleepy end device. All these routers are the same, except this one here, which was promoted to a leader. The leader is just a router who's allowed to promote people to routers. That way we don't have routers randomly getting promoted separately. You don't really pick your own leader, they elect their own leader, essentially randomly. But one of the routers will be a leader, and in this case it's number CC. So CC is a router, he has a child CC03. 7C is a router, he has a child 7C02. 98 is a router, he has children 9802, and he has a link to 4002, but that's not his child, that's actually router 4's child. So if this guy loses his link to router 4, he knows that he has another node in range, but he'll only actually talk to router 4 here. Looking at the packet capture here, it's initially kind of just the Wild West. These guys are broadcasting out to FF022, which is all routers in IPv6. Very normal IPv6 address. And they're doing a parent request. They're trying to find a parent on the network. So they've got some information here on their security. They're trying to find a network that matches their network configuration. So they just keep advertising out that they're looking for a router, or in this case they are a router, and what they're looking for. Over here in the back end of the simulator, I can essentially run a CLI from any of these nodes. So I'll pick node 1, for example. His state is currently the leader. And his routing table shows these routes to and from each other node. So the routing table considers the RLOC16, so this is the address of the other router. So 28, 40, 7C, 98, and CC. The next top is which node we go to. So to get to 28 or 40, we have to go via 31, which is this guy, 7C. So in this case, he's saying if he wants to get to 98 or 4000, he needs to go via 7C, and that makes perfect sense. Now another thing it includes in its routing table is this LQ. That stands for link quality. So when building routes in Thread, they take the link quality, which is the received signal strength indicator, RSSI, in both directions, and they compute a link quality 0 through 3. And that's used as a sort of cost estimate in the routing algorithm. So routes with a poor link quality have a higher cost. So we'd prefer to take more reliable routes, even if that might mean taking more routes instead of getting a short hop, a single hop that has a poor link quality. And going back over to the packet capture, once we've established a link, we send out these router advertisements. They're again going to FF021, so that's everyone, by MLE. So in this case, this came from router 9800. It contains leader data. Is he the leader? No, CC's the leader. And it contains all of these Route 64 objects. So this is essentially a list of all of the other routers, so in this case 10, 31, 38, 51, and the link quality for them. So that's going to be essentially their path cost. So by continuously advertising this, and we have zeros or threes, the simulator doesn't do like partial link quality. It's either there or it's not. So we don't have any 1s and 2s. But so we either have a link or we don't. And it's advertising its own link quality and its own cost for each of these routes. And this is very similar to the routing protocol RIP. And in RIP, we continuously advertise our own routing table out on the network, and everyone else builds their routing table by adding their own costs on top of ours. So whichever router this is, 9800, he's advertising that he has link quality to 10, 31, 38, and 51 at these costs. So when someone receives this table, they know what his routing table was, and they add their own cost to him on top of this to get a set of links if they were to go via router 9800. And if we receive everyone's routing table and do this addition on top of it, we can compute our own best routing table. So 9800 was the one that sent that out. So he had a connection to 4000 and 7C, and then he also had a route to these two guys, but it wasn't as good. So if someone had a better route, they might take theirs instead. Okay, so here I am to do the firmware build. I got one of my dongles hooked up. Well, I got three of them hooked up, but I got one of them hooked up to the build machine. It's running plain Debian with the plain kernel, not the cloud kernel, because that one doesn't have serial drivers. I've got instructions on my website, and you can just copy and paste this guide. But if you have problems, I also pointed you to the guide from Nordic and a couple of other guides. So let's see if this just works the first time or if it's all broken. We're hoping for the best here. It's kind of a lot of commands to copy and paste. You probably want to copy and paste them like one at a time so that if there's any errors you can fix them before just wrecking everything. So while that works, a bit of a description. You do apt update, we install some stuff we're going to need later. So Python, git, cmake, ninja. I don't know why they use both cmake and ninja, but they need both. Next up, we add ourselves to the dialog group, which is the group that accesses serial ports. We then install West, which is the build tool we need. We download NRF from Nordic Semi. We move it to user local bin so we can use it. Then we install some packages from NRF. Ultimately, we install this NCS toolchain 2.9.1. And then using West, we tell it to clone the Git repo. I have it doing main, but if you want to do a release version, you could pick a version like v2.9.1. Then we update, which tells it to download all the sub-references and stuff. Then we go in there and launch a toolchain shell. At that point, I make you stop copying and pasting so we can run West build within this NRF shell. So I get still downloading the toolchain because the toolchain is massive. Nordic didn't seem to do any sort of like optimization here. The toolchain is like 5 gigs or something stupid. But yeah, it's a huge pain. I did find pre-compiled examples for the NRF52840. However, they were for version like 2.4. The current version is 2.9, and that version didn't support the latest version of Thread. So you have to be on at least like 2.8 to get Thread 1.3 or 1.4, something like that. So I'm compiling it myself. If you guys want to use my build that I built today, you can download it from the blog post down below. It's all ready to flash right onto your board if you get the Nordic flashing utility. Now I'm flashing this thing on Linux with the NRF command line. They also make a flashing util for Windows and macOS that is a GUI. So if you'd rather do that to flash your Nordic dongle, you're welcome to do that with my binary. This is so slow. Forgot if I mentioned or not, I created a new VM just for this purpose. So I know I'm doing some things that Python 3 pip would not be happy with. That's perfectly fine because this VM serves this one purpose and that's it. This is very, very slow. So at this point, the NRF util is doing a git clone of basically every Git repository from Nordic Semi, all submodule into each other, and it's what we need to compile for the NRF52840, but it's a lot of stuff, so it'll take a little while. So anyone want to help me make like automation to compile deb packages of this shit? Because these, oh, it failed. Ugh. No space left on device. It filled my entire VM disk with crap. So anyway, does anyone want to help me set up some automation to compile this stuff into deb packages and to automatically compile the NRF52840 firmware images every time they release a new tag? I mean, I could do it every time they push to main, but probably every time they release a new version tag, it'd be good to compile it. I think they should just do that as part of their release, but they don't. Maybe because this is like example code from them. It's like a OpenThread example, one of their thread projects. But it's basically only usable like as is. You don't modify the RCP example, the radio co-processor, you just use it. I don't know. Okay, here we are, initializing shell environment. So from there we need to do, well, first we CD over to the coprocessor sample. Then we're going to do West build for the NRF52840 dongle. Then we're going to generate a package from merge.hex and output otbrrcp.zip. And finally we're going to flash that. So let's do the build. Okay, so now we have merge.hex. Next step is to do NRF package generate. Now we have that OpenThread Border Router rcp.zip. So finally that zip file needs to get flashed. If you really like using the Windows utility or the macOS utility, that is entirely an option here. You can build it in a virtual environment on Linux where the commands work and they're easy. Then you can take that zip file, flash it on Windows, or in my case, I'm flashing it through the command line on Linux. Also, we got to get this guy in bootloader mode. Now, if you've never flashed it before, it'll have a blinking red LED, and it's already in bootloader mode. So I'm going to unplug it. There's a button here that's not the reset button. There's another button that's sideways, right here. I don't know if you can see it. So I'm going to push this button, hold that button in while I plug it in, and then it should come up and start flashing its red LED. And that means it's in bootloader mode. So once it's in bootloader mode, we can flash it. It should be TTY-ACM0. There it is, TTY-ACM0. And this is actually a pretty quick process. And now we're done. If you have more than one dongle, you can just run this last command over and over again, program them all. For our purposes today, all of these guys are going to have the same firmware. It's called the Radio Co-Processor firmware. So all the hard work is being done on Linux, on the host. This is just doing radio, and so we have a whole bunch of different applications we can run with the same Radio Co-Processor firmware on the device. So next up, we got to set up the OpenThread stack. Now, the OpenThread daemon, which can act as a router and a client, that is actually easier to set up than the border router. However, we need a border router to kind of set up our first network. So I'm going to do the border router first. So once again, I have instructions on the website to copy. Basically, we're going to install Git so that we can git clone the OpenThread Border Router POSIX. Then we're going to set all the configurations we want as environment variables. So we're set up as a backbone router or the border router. We're not doing NAT64, THCPv6, etc. I'm enabling the web GUI and the API that Home Assistant needs. And finally, this is the interface that we route to. So ETH0 is the default. Obviously, you need to change that. OpenThread has scripts that will automatically set up routing. They're going to modify a lot of your IPv6 config. So if you rely on the kernel to accept arrays, for example, that'll get disabled here because we're enabling IPv6 forwarding. But the script should take care of everything you need. The script's obviously being bootstrapped and set up. So I'm going to copy this part of it here and run this without running the scripts. That way I can change the ETH0. So now I need to figure out what my infra IF name is. And in my case, it is ENS18. Let's go ahead and set that. Now that that's set, I can run the last two scripts. This should take care of everything. Now, if you're a big fan of virtualization, I have found the script to be very touchy on Debian cloud images. So I've been testing on a number of different Debian platforms here. I've tested on Raspberry Pi OS 64-bit, which is Debian-based. I've tested on Debian 12 and 13 installed from ISOs. Those work fine. And I've also tested on Debian 12 and 13 installed from cloud images. Those did not work. Now, even if I install the full generic kernel instead of the cloud kernel doesn't have really any drivers since cloud environments don't need them. I still don't get this script to work properly. So some of the files this is touching that involve networking are just not there on the cloud image. So the Debian full images seem to work fine for Debian 12 and Debian 13. Now Debian 13 hasn't exactly come out when I released this, so I guess it could change in the future, but this script at least seems to work fine on Debian 12 and 13, the single board computer version Raspberry Pi, on ARM, as well as on x86. And over here is actually compiling, so it looks like it's almost done. Now when this script finishes, it's going to try to immediately start the OpenThread Border Router on TTY-ACM0. So if you have more than one USB serial device, this might break things. I recommend not plugging in the dongle until you figure out what port it's on, then restarting the service. So I plugged in my dongle, and now I'm going to do ls-la dev serial by ID. So this tells me I have USB Nordic Semiconductor ASA as TTY-ACM0. Now if this is just doing a thread border router, this is fine. ACM0 is the serial port. However, if you're also doing Zigbee, Z-Wave, any of those other things, they're probably also going to be a TTY-ACM, and you can't tell which one's going to become 0, 1, 2, 3, etc. So then we need to use the path from serial by ID. And we need to add this file, etc default OTBR agent. And I'm also going to copy this long path here from dev serial by ID. So this is the configuration for the border router agent. we need to set this agent ops here. So see how it defaults to spinal, HDLC, UART, dev T2I ACM0. So I'm going to change that to dev serial by ID / my very long string. So this way it will be bound to this specific dongle and not whatever serial port it finds. And now we can start up the service. So I started both the agent and the web interface, so let's take a look at the web interface now. So this guy just chills on port 80, so you don't even have to specify a port number, just HTTP and the IP address. So this has got a pretty cool UI here. We can see the topology, etc. Currently we don't actually have a network, so we have to go to form and create a network. OpenThread defaults to this very common security key, 00112233, etc. And that is done so that their examples can do packet capture by decrypting the packets, which makes it very nice for debugging, but you probably do want a real security key here. And now in topology, I am the leader and I have no other nodes. So now at this point, our thread network is set up. This border router node should be broadcasting the thread prefix onto your IPv6 network as a whole. So all of your IPv6 clients should find a route to the /64 of your thread network show up in the routing table. At this point, we're ready to continue on with clients. So now, for nodes which are not border routers, they're just acting as regular nodes in the thread network, it's a lot easier to set up. So instead of running OT-BR POSIX, we're going to run OT daemon, which is part of the OpenThread build. This will just create a tunnel interface on the system, WPAN 0 probably, and it'll let you join the network, do IPv6 over the network, act as a router for the network, etc. It's just not going to enable routing on your system, so it's a lot less disruptive to the client system. Once again, instructions on the blog. We're going to add git, we're going to git clone the OpenThread repo, we're going to bootstrap, and we're going to build. We don't need any sort of environment variables this time, we just need OT daemon on. So let's go, and we're off. So next up I'm going to run the daemon in verbose mode manually just to make sure it's working. So T2I ACM0 is my serial port. Again, change that if you need to. So let's go ahead and run that guy. Oops, sudo failure. There we go. So this is going to take this terminal, so I opened another SSH session to the same system to continue. So next we're going to get a little bit familiar with OT control. This is the OpenThread CLI, I guess you call it. And the border router had this as well, but we used the web UI instead. So if you do a lot of work with OpenThread, the OT control CLI is going to be really important. So since we never copied it anywhere, it's still in our build folder. I'm going to sudo this. So there we go, we should be good. So if we ask for state, it says disabled because it's not running. So coming back over to the border router now, we need to dump the network state so that we can add our new client here onto the network. So if I run dataset active, it'll show me all the data. And this is all the data we need, but if we say -x, it'll give it to us in a binary format that we can just copy and paste. So coming back over to the client, we can say dataset set active and then the big blob, and that should be set. Obviously, you can provision your devices you've bought through Home Assistant. That's the easiest way to do it. I found for devices running the OpenThread daemon like this, it's easiest just to copy and paste the data set. You just get the whole security blob at once. So next we do ifconfig up, followed by thread start. And hopefully nothing crashed over on this side. Looks like we're good. Then we can run IPAddr. So we got our IP address, FD1122, that's the default. And we got a IPv6 address off of that prefix. So coming back over here, this node got promoted to a router. So this is me, the border router, and then this is the other one I just added. It got promoted to router, and its external address is 4AC4, etc. And that matches this address here. By the way, all nodes initially join the thread network as a child, unless they're the first node, then there's a leader. So if your guy shows up as a child, not as a router, just wait a little bit and he'll promote himself. And finally, if you want to run this guy as a service, I've got a systemd unit on the blog. You can copy and paste and see the instructions there. So now I've got a mesh set up with a border router upstairs. I've got a client which is acting as a router in my kitchen, and I've got another client acting as a router down here. And so now I can send packets from down here via the router in the kitchen upstairs without having signal range. And that's one of the really cool things about Thread, is that it forms a mesh between every node that's capable of acting as a router. But at the same time, It lets low power devices turn off and not act as a router, and their corresponding parent router will deal with packets and routing for them. What I can also do is add a second border router in the mix. So with the second border router now, both of my routers down here and upstairs will be able to route across Ethernet as well. Here's my topology now. So this is my border router upstairs. This is my client in the kitchen. This is my client downstairs, and this is my blinds. So I'm going to take this border router and replace its data set with this one, and it will join the same network. There is the data set. There we go. Now we magically should be on the other system. So Thread can also work with different partitions where the network gets separated and then the two sides can't talk to each other over the radio anymore. Then they still share the same network credentials, but they're trying to create a bridge back between them. That could be what's happening here. So my new border router hasn't found anyone yet, so it thinks it's on its own partition. But once it finds someone else that's on a different partition, it'll delete its partition and join the other partition. There we go. So I think this one is the new border router. Every time a node joins, it's initially a child. If it's capable of being a router and there aren't at least 23 routers already, it might choose to promote itself over time. That takes about 2 minutes. So the Thread network tries to have between 16 and 23 routers at a time. It can have up to 32. And so this node joined as a child, and now it needs to get promoted to a router for it to do routing. Okay, so we have R and R. That's my two routers in the kitchen and in the downstairs. This is my new border router. It is still a child. Okay, so they have meshed themselves now. This guy is my first border router. He's the leader, 4D2049. This guy here, 4A, is my downstairs client. And it looks like he's got a route to everyone, so he's got pretty good signal. This guy over here, C681, he's in the kitchen. He's also got pretty good signal. And then this guy down here is my downstairs border router, and he can get to the other two routers, but not to the first border router. And that's fine. So from here down on the bottom border router, I can ping the other border router directly. Another neat trick here, so I'm on the border router, and if I look at the IPv6 routing table, you can see this is the mesh local prefix, so this is communicating within the mesh, dev WPAN 0. But we also have FD1122, that's my off-mesh prefix, via WPAN 0 metric 256. But this is the other border router here, so we can also get to the same off-mesh prefix, FD1122, via the other border router with a higher metric. So if I didn't have this WPAN 0, I would see two different routes to the same prefix via the two border routers. And by the way, these border routers found each other across the Ethernet network via MDNS. So it should be entirely automatic. These two border routers are on the same network, and they'll find each other and be happy. So now, having gone through all of the work to set up my Thread network, what do I think about Thread as a protocol and the future of Thread? So first off, OpenThread is essentially the protocol stack that everyone doing Thread is running. Developed by Google, it's open source, BSD licensed. All of the different vendors that I've looked at their SDKs for are all using OpenThread to implement the Thread protocol on their chips. So Nordic has used OpenThread as part of their thing. So has Silicon Labs. Who else does it? Espressif, the new ESP32s, they're using OpenThread as well. So it's pretty common out there. I'd like to get in to try to make my own Thread devices. I thought about trying to compile my own application for the Nordic dongle. They'll be self-contained, and I'm just out of time in this video. So I'll have to make another video if you guys want that in the future. I've also thought about trying the ESP32, I think it's the H2 that has built-in 802.11.4 radio and supports Thread. So that would be another target as well of mine. Of the devices in my house that could support Thread, I think a lot of them would probably be better off on Thread than on Wi-Fi, for example. So like I have a bunch of smart plugs, things like that. Those don't really need to be on Wi-Fi or Thread. They can kind of go either way. They're powered by AC, so they're not battery constrained, which is where Thread devices really shine. I have my blinds over here, made a video on those up here when I talked about Matter, and they run on Thread as well. So I like those, obviously. They work well for me, haven't had any problems yet. So the places where I'm really excited to see Thread are in my light switches. So I already have light switches that I have one that uses Zigbee and I hate it. I have a bunch that use Z-Wave and they're really reliable. But Z-Wave is like a very old school mesh network. There's one controller that computes the routes for everybody. There's a command you can run on the controller to call heal, where it will rebuild its routing table, interrogate everyone on what their link quality is, things like that. And Thread just deals with all of that better. Thread also carries IPv6, so I don't have to deal with a border gateway anymore. With my Zigbee and Thread, I have a video up here on my Zigbee and Z-Wave. Video up here on my Zigbee and Z-Wave radios. And those both need to run software that translates application level data, like light switch states, percentages, sensor value stuff, from the Zigbee carrier onto some other protocol, because the data encapsulated on Zigbee and Z-Wave was never intended to leave the network, really. It wasn't intended to route. And so now with Thread, we don't have to worry so much about translating all this data at the protocol borders anymore. We can just carry the IPv6 packet straight across and let the application layer deal with IPv6 like it's designed to do. So long term, essentially, all the devices that I have on Zigbee and Z-Wave, I would like to move to Thread if I replace. I'm not going to replace them all just to do this, but that's where I would like to be going. So this is things like light switches. I have a fan here, my blinds, door locks would be a great candidate for this. They might be fine on Wi-Fi too, but Thread is a simpler network, better for battery-powered stuff. All my sensors, I have some sensors up there. Where is it? I lost it. I had a temperature sensor up there on my bookshelf. Battery probably died or something. It's Zigbee. I hate those things. If I could find some nice Thread temperature sensor, I'd be very happy. So what about Thread outside of home automation? Well, outside of home automation, in sort of a more industrial automation sense, 802.15.4 kind of sort of promises a longer range than Wi-Fi, at least compared to 2.4 gigahertz. So on 2.4 gigahertz, I think it's using it has 5 megahertz channel spacing compared to 20 megahertz for Wi-Fi. And they're using a much simpler encoding type. They're not using QAM, they're using BPSK. And so it can tolerate noise a lot better, I guess, because you're not sending as many bits per symbol. Like in Wi-Fi, they're trying to fit 12 bits per symbol, which is a huge amount of bits to pack into a single sine wave, essentially. So with Thread, they're only packing 1 in. But if you actually need to carry IPv6 in a more industrial setting, there is a Wi-Fi version that runs on 900 megahertz, and that is called, what is it called? Halo, 802.11ah Halo. So that is great for like a traditional AP to client topology where you put APs around your facility, you've got stuff talking to it. Thread has been used more successfully in places where the mesh topology is actually really useful. So Thread is based on a protocol called 6LoWPAN, which is where all of the IPv6 header compression was developed by the IETF. They developed their own routing protocol called RPL, and it's different than the routing protocol used by Thread. So Thread developed a protocol called MLE, Mesh Link Establishment, that does a distributed Bellman-Ford routing algorithm, which is very similar to RIP, if you're familiar with RIP. Very, very simple routing. So that's what Thread uses between its 32 routers. And they simplified a lot of the router counts and things like that to make it easier to pack them into IPv6 addresses for locating purposes and things like that. 6LoWPAN does scale better. There's an article that I've referenced a couple times now of a sensor network in the Scottish Highlands where they had probably, I don't know how many. I've heard that there's networks up to thousands of 6LoWPAN devices in the same network. I'm not sure if that is smart meters or the Scottish Highlands, but one of those two articles I read about that. And essentially they have a whole bunch of sensors. I think they were measuring like water flow in streams or water temperature or something like that. They had sensor clusters in streams, a little solar panel, a little battery, and they could just have like hundreds of these all the way up the stream. And because they're in like a line down the streams, they can all talk directly to their neighbor, and then they can go all the way down the stream to the very end one that has cell service. And so then they can have hundreds of these sensor nodes relaying IPv6 packets for each other. They're not sending much data. They're sending data back like every hour. But they have enough bandwidth across their mesh to send data really long distances by hop, by hop, by hop, by hop, by hop, by hop, by hop. And the same thing is used for like smart meters. The smart meters can talk to each other. If you have like a gateway somewhere, then all the smart meters are probably close enough that they can relay from one to another to another to another about energy usage. And that's not updating that fast. They only have to send data back like every couple of hours, so it's not hard. So anyway, those are my opinions on Thread, 6LoWPAN. I think Thread is a better designed network than 6LoWPAN for the scale they're trying to target. So they specifically kind of said the RPL routing protocol didn't scale down very well. It caused a lot of traffic in figuring out these routes. And so they wanted to use a simpler routing protocol. That's why they developed MLE, which uses distributed Bellman-Ford, one of the simplest routing protocol algorithms. And they're designing this for like the scale of a single large residential, like it could scale out to quite a large house or a small business, not to 1,000 sensor nodes in Scottish Highlands. So anyway, thank you again to Brilliant for sponsoring this video. Go check out my link in the description down below, brilliant.org. If you want to chat with me more, I have a Discord server link down below for that as well. You're welcome to message me there. And as always, I'll see you guys on the next adventure. All the commands are in the blog post as well, down below for that also. You're welcome to copy and paste. I also have the firmware that I've been using for the Nordic dongle if you want to use the same Nordic dongle as me. It's kind of a pain to compile, so you might want that. No guarantees on that, but it's available. So yeah, I'll see you guys on the next adventure.